Hi, you guys. This is Mrs. Lorenz. Hopefully, you took some time in your groups to discuss the first 4 questions on this worksheet. So I'm going to go through those somewhat quickly since you've already had some time to kind of think about these questions. And then we're going to use these same questions to introduce something called function notation today. Remember, we're starting our new unit on functions. And so I know I haven't been there to introduce that yet, but this is just the first step of that, just kind of understanding how to, a different way to write them that you may not be used to. So this problem was all about how long does it take to stop your car? And that's dependent on how fast you are going, which of course makes sense, right? The faster you're going, the longer it's going to take to stop. So question 1 could have a variety of answers. There's not a right or a wrong. What are the factors that you think affect a car's braking distance? What would impact that, right? How fast you're going, what kind of car you're driving, what kind of condition your brakes are in, or like if you have tires that are not so good, that might take longer to stop. What kind of road you're on. If the road is in bad condition, that could take, right? So any of those things are okay. Just to kind of think about, there are lots of factors that impact braking. And then we start to look at this relationship between a car's speed and the braking distance. So they gave us the information in a table, and then they also plotted it for us, right? So like 0, 0, and then 2019 is here. They left this one as a question mark, so I filled in, if you come here to the speed of 40 and follow the graph up, it looks like about 75, and then 60, and they estimated this right here to be 171, and then at 80 we're up here, and they say that's about 3. Oops, I'm on the wrong line. I think 80 is actually one more over from that, I guess. So 80 would be about here, which is about 305 feet. So then we're just going to answer some questions about that. So what's the braking distance of a car? 60 miles per hour. Again, you could have figured that out from looking at this right here. So 171 feet. Or you could have figured that out from looking over here at the graph. If I come over to 60, looks like they're saying 171. What's the braking distance for 40 miles per hour? And again, you had to kind of make an estimate of this because there's 40, and it originally was not in the T-chart. I went ahead and said it looked like about halfway between 50 and 100. So we're going to say 75 feet. How do you know? So I know because the graph shows the Y value is approximately 75 when the X value is 40. Right? That's a really important thing to understand. This horizontal axis is X, and this vertical axis is Y. So then it says, what does this ordered pair 73 to 54 represent? So, or what does that point tell you in the context, right? This is your X, and this is your Y. So it tells me that when the car is traveling 73 miles per hour, it will have a braking distance of 254 feet. Then it says, what if the car took, it took 400 feet to stop, right? So 400 is the braking distance. Estimate the speed. So I said 65 miles per hour. How did I figure that out? If I come up here to 200, this is what we know the braking distance is. There's where the graph is 200. So now I have to figure out what is the speed there. So if I follow this down to X, that appears to be 65 miles per hour. Okay, so let's just go back here a little bit before I move on to questions 5 and 6 and talk about function notation. We'll write some notes down. Let's just go back a little bit here and let me talk about it through these right here. So when we talk about a relationship, right, that's generally going to be a function, right? A function is just an operation or a rule that pairs two things together. It shows a relationship, in this case, between speed and braking, or X and Y, okay? So here's what function notation will look like. We would say f of speed equals the distance would be one way to write this. In other words, if I call the function f, that's just the name of the function, right? We put speed into the function and it gives us back distance, right? I tell it what the speed is, and then the function tells me how long it takes that car to actually brake. And so this is just the name. This, whatever I put here is the input, and whatever I put here is the output. And we'll write all this down in a little bit, so it's okay if you don't get everything. I know there's not a lot of room right there. So for example, this one right here, another way to write this question and answer would be that at f of 60, in other words, I put 60 miles per hour into the function, and it gives me back 171 for the distance. Or at f of 40, that means what is the speed at what is the braking distance when the speed is 40 miles an hour? I get back out of that function 75. Over here, when the speed was 73, I put 73 in, and I get back 254 feet. Okay, let's try to write this one also. F of 65 is the speed is 200. Right, so I put speed, I'm just going to put an S for speed in, and we get back distance. It's just telling me what the relationship is. It's telling me what I'm putting in. It's telling me what comes out, and it's telling me the name of a function. So let's look at 5 and 6 together, and then we're going to capture some notes as well. So find f of 80 and interpret the meaning of this value in the context of this problem. So they're saying that the speed is 80, and we want to know what the distance is. So f of 80 is going to be equal to, let's come up here, you can look two places. You can look on the graph, or I think it's right here in the chart also. It was nicely put into the chart for us. At 80 miles per hour, it's 305 feet. Okay, so if I'm asked to interpret the meaning, a car going 80 miles per hour will need 305 feet to stop or to brake. Okay, number 6, use function notation to express that a car traveling 45 miles per hour will require a braking distance of 96. So they're just asking us to write this like we wrote this one. I don't have to interpret here, right? This one said interpret, which means say what it means. This one's just write it in function notation. So f of the speed equals the braking distance. That's how we would write that. And it's a much quicker way to basically say all of this, right? It's telling me that when the speed is 45, the braking distance is 96. Okay, so here in the notes, I want to just capture a couple things that we just talked about and what some of these things mean. And then we're going to do a couple other practice problems here. So some things to jot down. Functions are rules applied to an input to create an output. And we often will write it like f of the input equals the output, right? That's just telling me that I'm plugging something into function f. And we don't always use f, by the way. Sometimes we'll use g or h or k. It's just the name of the function. And often you'll see this, right? X is generally the input. Y is generally the output. X goes into the function, y comes out. Okay. A couple other things, and you guys can pause this, of course, if you need to slow down and capture some of this. When we ask you to evaluate a function, evaluating means find the output for a given input. I'm just going to make an example here. Let me say evaluate or find f of 3 means find the output if 3 is the input. And there might be different ways that we find this. We might find these things from looking at a graph. We might find them from looking at a table. We did both of those things a moment ago with the braking distance. We might eventually, we'll do it with an equation, but for now we're mostly looking at tables and graphs, okay? So what I'd like you to do now is give some of this a try with your groups. The check your understanding on the back here. This is just classwork. So we're going to pause the video and then start it back up when we've all had a chance to try these and see how we did. Okay, so hopefully you've given this a shot in your groups and you've talked this through. F of -2 means x is -2, and I want to know what y is, which would be the output. So if I go follow this graph up, it says that when x is -2, y is 2. And then it says find f of 1. So here's where, again, that's your x right here. So x is 1. We're going to follow this up and figure out that y is 3. Part C is backwards. It's telling me the output. So that's like my y value, and we want to know what the input is. Notice they used A for the input. It doesn't matter. You can use different variables. A lot of times we'll use different variables to represent different things. But either way, this is the output. So let me go up here. Here's where the output is 6. So now I need to figure out what was the input. So let me just follow this back down. I'm just kind of using this graph backwards now. That means A was 5. When I put 5 into this function, right, it shows me right here, when I put 5 in, I get 6 out of the function. Okay, this one is n of t. They used a different variable for the name of the function because it stands for number of people, right? That n is just the name. The t is telling me that this is a function of time. So we put time in and we get number of people out, right? Time is input and number of people is output, like what comes out. So they're asking me to interpret, which means I need to write a sentence about each scenario. So this is saying, again, this is on the inside, so it's the input. So 1 hour after opening, right? This is a food truck. 1 hour after it opens, 11 people are in line, right? This is the number of people in line at a barbecue food truck. So n of 4, again, that's an input, means the number of people after 4 hours. And this means the number of people after 6 hours. So what this sentence is saying, or what this inequality is saying, is that there are more people in line after 4 hours than after 6 hours. Okay, moving on to the next one. This means 0 hours, and this means 3 hours, and it's saying they're the same. So the number of people, oops, let me erase that, in line, well, 0 hours would be when it opens, and at 3 hours is the same. And then this last one's a little weird because they didn't give me a number for the input. They did give me an output, which is people, right? So 34 people in line, but I don't know when. They just told me R. So I'm just going to write it in terms of R. Okay, so there are 34 people in line after R hours. Okay, let's take a look at this last one. Physicists have discovered that there's a pattern or rule, right? That's what a rule is a pattern that can determine the braking distance based on the car's speed. Take the car's speed, whatever the speed is, we're going to square it, so to the second power, and then divide that result by 21. Use this rule to predict the braking distance of a car traveling 90 miles per hour. So we're supposed to take the speed, square it, and divide that by 21. So take your calculators, go ahead and do that. See what you get. Should come out to 385.7 approximately feet. So now we want to write an equation for that function, right? So it's saying for f of s, that represents the car's braking distance when driving at a speed of s miles per hour. So that's the input, or the speed. And they just told us here what to do with the input. They told us to square it, like we did here with 90, but this time it's just going to be s. And then they told us to divide it by 21. So that's my rule or my function for finding braking distance when we know the speed. Okay, that's the conclusion of our notes. Now you're going to get your CYU for the day that you can practice this a little bit more on. And I will see you when I return. Be good.